All right, good morning or good afternoon, everyone. Welcome to this webinar on coolant selection for data center design. Let's give it one more minute so that we give everyone the chance to join. All right, let's get started. So good morning and good afternoon, everyone. So I'm, as you probably all of you know, I'm Lieven. I'm founder and CEO of Diabatix. I have the pleasure today to do this webinar together with our friends and colleagues from Arteco. Next to me is Vadim. He will probably introduce himself during the next few slides as well. And later on, you see also one of our colleagues pop up and take over during the talk. As usual, this webinar is live, but we have opened the chat so that everyone can ask questions either in public or through the private chat throughout the webinar. It's not always the easiest to answer them immediately on the spot. So if your question is not answered throughout the presentation, throughout the webinar, don't worry. At the end of the session, there's also a Q&A. So then we will answer the questions during that part of the webinar. If in the end the question still remain unanswered, then we'll follow up with you over email. The whole webinar is recorded, so everyone will receive a recording of this via email somewhere the next few days, so that you can rewatch it have it for future reference. So with all of that said, I think we're ready to get started. So welcome everyone on this webinar on, I titled More Than PG25, the Influence of Coolant Selection on Data Center Design. And as the title might already give you the indication, this webinar will be discussing primarily the influence of coolant selection on data center design or on thermal design. We from Diabatix are, of course, very interested in this type of topic, because our starting point or the way we operate is through the use of smart algorithms, very advanced models, and so on, to help engineers design design the next step of what thermal management has to offer. As you will see during this webinar, coolant selection has, of course, and obviously a very big influence on this. That's also why we are very proud and happy to say that Arteco is one of our technology integration partners, helping our customers together with us, bringing this the influence of coolant selection closer to the design engineer. And this webinar is one of the aspects of bringing everything closer together. So the way we approach it from Diabatix point of view is through the help of simulation and design support. We still do that through our ColdStream platform, which is basically worldwide the #1 generative design platform for cooling. We'll also illustrate throughout this webinar what it means exactly. If you would like to explore, if you're exploring coolant selection and the influence on the design process, we have a few very nice examples of that coming up toward the end of this webinar. Without further ado, I would like to pass the floor to Vadim. He will introduce briefly Arteco. Voilà.
So my name is Vadim Vermeeren. I'm business development manager for Arteco, specifically for the data center sector. Arteco is a pioneer in coolant solutions, water-based coolant solutions for a variety of markets. It all started within automotive, but we do provide solutions for data centers, but also other applications. It's more than 25 years ago that we pioneered technology that we are also using now in the data center. We are a joint venture of two big oilcos, Total Energy and Chevron. We are a global player, and in our market segment, we are a market leader. One important thing to note is that we are an innovative R&D focused company. That's also why we partnered with Diabatix to see what we can do beyond the current specs of what is now required in data centers. So if you look at how we see the market today and also for the future, a lot of things will be still air-cooled. But where we see ourselves within the market is that for the high performance and the AI data centers, the go-to currently is direct-to-chip liquid coolants. And we find it important to see what the current PG25 can do, but also what, with innovative coolant solutions, the future could bring. On the next slide, we see here the typical solutions that we have. So first column is air-cooled, direct-to-chip. Then we have immersion, single-phase, two-phase immersion, and two-phase direct cooling. The current market need is around 500 watt to 1,000 watt. That's also the sweet spot of where PG25 could be. But we believe that with future innovation, we still can also have water-based solutions that could cool chips more in the future. With that being said, I would like to also switch sheets with Senne. Senne is our technical manager at Arteco, and he can explain how we will do this.
All right. Hi, everyone. So we'll have a look at the current ways of cooling chips in data centers today, being, of course, still a lot of air, but also water, and then the propylene glycol, which is usually referred to as the PG25 type of product. And if we look at them from a thermal conductivity perspective, which is actually the capacity of a fluid to transfer the heat, then we see that water is there, the best in class. It's the best product you can use today, at least with the current technologies at hand. Same goes for the specific heat, which is the capacity of a fluid to absorb heat. And if you look at the viscosity, which has an influence on the pumping efficiency, the power needed to pump the air, the water, or the propylene glycol, then you see also there that actually the propylene glycol is more viscous, so it takes more energy to pump it around in the system. If we look at other characteristics like the freezing point, for instance, then we all know that water already freezes at 0 degrees, so it takes something extra added to the water to lower the freezing point. On the corrosiveness, water, as we all know, is in itself corrosive to any metals, and the same goes for the PG25 type of product, which has also a lot of water in it. So it takes some additives to protect any of these materials from corrosion that might happen. The biofouling is so the growth of microorganisms in the cooling system. It's a huge concern today. It's less or no risk with air-cooled systems, but it's a big concern for water-cooled systems because the temperatures that the cooling systems are running at for data centers is in a range that allows microorganisms to proliferate. And by proliferating, they actually form a biofilm on your cooling system, preventing the heat from properly being transferred. And they might also start to block any narrow channels. So with a pure water-based product, you could get the biofouling. It would allow any microorganisms to proliferate. And that's actually also the reason why 25% of propylene glycol is being added to the product to prevent that from happening. And then on environmental impact, well, if you look at the sourcing of the material, air, water, of course, there's no issue with that. Propylene glycol, on the other hand, is derived from a fossil fuel still today. So in a nutshell, on the current ways of cooling data centers today, well, we know that air has a limited heat transfer and a limited heat capacity. On the other hand, water, it has the best heat transfer capacity and the best heat transfer and best heat capacity, but of course it's corrosive, freezes at 0 degrees, and gives this issue with the biofouling. And that's the reason then why the PG25 is there to lower the freezing point and to prevent any biofouling from happening. Now, if you look at any future trends, because that was the situation today, if you look at any future trends, then we see that the compute power is going up. There's no doubt about that. And with that, also the heat output is going up. There's also a need for a better thermal efficiency because of that. But on the other hand, there's also a move or a focus towards lower energy usage because of this metric, the PUE, the power usage effectiveness, which is actually the ratio between the energy being consumed by our IT equipment compared to the energy needed for the entire data center. And there's also something like heat reuse that is coming up more and more, which is actually the use of the heat that is being generated by the chip for other means, like heating up swimming pools is something that is much referred to now these days, but it could also be district heating or something else. And the solutions to solve all these things for the future, as it looks today, could be three things. Could be three technologies. There's on one hand the two-phase approach, so the phase changing from either a liquid to a gas or directly from a solid to a gas. You have the immersion technology, which is actually immersing the full server into a dielectric fluid, so no electrical conductivity there. And there's also the water-based coolants, which also still have a future. If we compare them on thermal performance, then the two-phase is the best in class when it comes down to heat capacity. There's no better technology than two-phase in terms of heat capacity. Immersion, on the other hand, is very good at cooling the entire surface because everything is just submerged in the fluid. So all the heat being produced by the server itself, it's all being taken away. And water, on the other hand, has the best heat transfer. So there's no better fluid that can transfer the heat better than what water does. If we look at the other parameters, maintenance, cost, and adoption, then still two-phase and immersion are in the adoption phase. It's still in the developmental, and there's still a lot of challenges. It's also more complicated designs that are needed compared to water, and that's why we see today still that water is deployed at scale, at volume, because everything has already been worked out. The maintenance is there. The DC operators are used to be working with this type of technology. The cost is low because it's there's low complexity, and of course the adoption is also a reason. An effect of that. And that's also what we see here. So the high compute power that is expected to be there in the near future probably could be solved with water because of its high heat absorption. The heat reuse aspect, so that taking away of the heat and transfer it to use it somewhere else, could also be solved with water because of its excellent thermal transfer capacities. And the pumping efficiency is actually something that can still be improved. Taking a fully water-based product has a much lower viscosity, but also by improving the design of the cold plate, you can still win and on this level. Combine that with the scalability through or an already adopted technology, and a lower capex and opex, well, through a lower complexity of the whole system and the fluid, if you compare it to the two-phase and the immersion fluid. Now, if you could add to that also the aspects of metal corrosion protection, material compatibility, elastomers, plastics being present in the system, and also solve the issue, the concern around biofouling, then you would have a product that is fully fit for the future. And that's also what we have done with our ZITREC EC10, our fully water-based product. This product has proven itself already to be fully material compatible. We've done extensive testing on all sorts of metal alloys and also on all sorts of elastomers, and all results were very good. And also on the level of biofouling, we've checked this product, which is fully water-based, has no PG in it, and also have no biocides. And also there we see a biostability over time. If you look at the thermal performance, comparing the fully water-based product with the PG25 that is most adopted in the field today, then we see a much better specific heat, which is the capacity of absorbing the heat with the fluid. We also see a much better thermal conductivity, so the transfer of the heat through the fluid. And you can see that also the viscosity is much lower, which has a very positive effect on the pumping efficiency. So there you go. That's on the fluid. And there's also a few things to say about the cold plate design.
Yeah, thank you, Senne. So yeah, if we want to explore now what the impact of coolant selection on the thermal design is, you need obviously a system that can support this this question. And that's exactly what we have developed with Coldstream. And so Coldstream, as you see here on this this graph, combines multiple different building blocks, modules. The one that many of you are probably familiar with is the simulation engine, which basically, if you give it give this engine a particular design, it will predict what the thermal performance will be, what the thermal resistance is, the pressure drop, and so on. What we have done within Coldstream is couple this simulation engine with the shape generator, which can, in practice, generate anything from pins and fins all the way to gyroids and other TPMS structures, or complete freeform shapes. The whole the control of this shape generator is done through the generative design engine. Not going to go too much into depth on how that functions exactly. We have different webinars for that, some other resources you will find on our website about it. But the main idea is that we have a self-learning system that learns from the simulation output given a series of designs, and through that learning process, it can control the design process itself. We couple it obviously to some manufacturing constraints, so that whatever is designed can also be manufactured in practice. And most importantly here, this whole system, especially the simulation engine, can be linked to a material database, which since 2 months also contains some of the coolants of Arteco, so that our users and yourselves obviously can select these coolants to see what the impact is on the design. So to illustrate a little bit more on what the impact is of these of the coolants on the physics itself, I briefly listed here again the Navier-Stokes equations. Probably for some these are familiar. For others, don't worry about it if you don't fully grasp what you see here on the screen. But what I most importantly wanted to highlight is the 4 key parameters that quantify a fluid from or a coolant from thermal perspective. The density, the viscosity, the conductivity, and the heat capacity all have a direct impact on the conservation loss. And so you can see, for instance, in the conservation of momentum equation, the direct link between the viscosity and the pressure drop. And similar for the conservation of energy, there's a direct link between the heat capacity, the temperature, and the conductivity, and obviously also then the heat source. Do note that all of these properties are temperature dependent, and so there is a tight coupling between the energy equation and the momentum equation and conservation of mass. But no worries about that. That's all pretty nicely taken care of by Coldstream, all fully automatically. So this is about from modeling point of view. What the impact is of the coolant. Obviously, we should also select, or we should also control what is designed for. Within Coldstream, you can design many different ways. The two most important ones are either through what we call standard designing or template-based designing. The other one is through complete freeform designing. For this webinar, we focused on the standard designing, focusing on three particular shapes that are highlighted here on the screen now. So we selected, on the one hand, gyroids to a gyroid-based heatsink, a heatsink that will be constructed with pins, and one that is constructed from fins and skived fins. This choice is obviously not random, because the skived fins they have the property of maximizing contact area, which triggers certain coolant, let's say the flow modes, and pushes more towards the laminar flow regime, while pins trigger turbulence more easily, and these gyroid shapes have a high mixing effect. So each of these shapes operate on a different way, and the question we want to answer is, okay, how does the influence of coolant selection, or the properties of a particular coolant, how does it affect the design? And can we still draw the same conclusions then at the end, independent from what the actual design was? To answer that question, we're zooming in on this water block case. So it's one of Diabatix more standard tutorial cases, which is a generic water block cooling a CPU or a GPU. We modeled, in this case, we modeled it for a cooling 500 watt chip, but you can use it for other operating conditions, obviously, as well. Consists of a few parts. Most important are a copper cold plate, a fluid region that contains a design internally, and then the housing around it. So let's zoom in on a little bit deeper on the water block. So you will see here the heated power or the heat input is not uniformly distributed, as it's split in three sections. For this study, we're actually comparing three coolants. On the one hand, a generic PG25, with properties we found, properties are publicly available, and compare that to Arteco coolants, EC10 and the EC20, where, if I'm not wrong, the EC20 is exactly the same as the PG25, and the EC10 is then the coolant that Senna briefly discussed earlier. So we have, obviously, when you make a design, also need to explain the system, what to design for. Obviously, for chip cooling, it's 9 out of 10 about minimizing the chip temperature for a given pressure constraint. So that's important to understand, that for the design process itself, regardless of the designs that are selected for the comparison, they all will be designed for minimal chip temperature for a given pressure constraint. Meaning, if you give it 3 different coolants, if the coolant has a lower viscosity, it will allow to change the design into something else to end up again at a pressure drop of 7 kilopascals. Voila. So as mentioned, there's within this this case also a design region present. The design region is highlighted in green on the screen. This is the part that Coldstream is allowed to change. Obviously, this is, again, a very generic approach that we take here. We're not aiming at designing the best CPU cooler for this case. It's the aim here is to study what the influence is of coolant selection on the design, and how that is linked to performance. So, but what we do for that, to answer that question, is we define the design concept, as mentioned in the previous slide, and those design concepts are filling the design region with a gyroid, with pins or with fins. We link it to a manufacturing method. And so for gyroids, obviously, that's in 3D printing, where we take some generic or the current state of the art of printing, compare it to a similar methodology for the pin product manufacturing, and skiving for the fins. We execute the design generation and optimization, and we do then analysis of the best concept. That's basically what you can expect. You see here on the screen, voila, immediately for each of these design regions, you see the optimized design, but let's also zoom in a little bit more on the analysis. Voilà. So what you see popping up now are for all different configurations that we made. You see the evolution of the optimization process and the design process of Coldstream. You see in total more than 1,000 designs being created. Remember, we have pins, fins, and gyros that we're comparing. We have 3 coolants, meaning that in total we have 9 different combinations that can be created, resulting in more than 1,000 designs evaluated in less than 2 hours. What we do next is select the best of each of these combinations to see what the impact is. One of the typical outputs, and that you see here, and we're not going to show this output for all 1,000 designs. So this is just one illustration. One of the typical outputs is the flow distribution, the heat map inside the design, on the outside of the product, and so on. And all of this information together allows them to evaluate the pressure drop, the thermal performance, and to make an assessment: is this which design is now the better one? And the image you see here are then is an analysis for one of the gyroid cases that were created. So, but what's I think what's most important to zoom in on is this design performance comparison. So you see here actually in this graph the temperatures, or the predicted temperatures for the milled pins, the 3D printed gyroids, and the skived fins. And every time you see one of the 3 bars significantly lower than the 2 others. And I don't think it's a spoiler anymore. I think everyone understood already that the PG25 and the EC20, which is basically the same as the PG25, have the same performance, while the EC10 is the one that has a significantly lower temperatures, so significantly higher performance. So remember, this is again for exactly the same operating conditions, meaning same flow rate, same pressure drop. The only thing we changed is the coolant, and looking at the thermal resistance of the heat source, of the chip itself, we see that in all 3 cases, independent from the design itself, we see that the performance increases by approximately 20% when switching from a PG25 to an EC10 coolant. So, and that combination, so that improvement comes from two elements. On the one hand, you have the lower viscosity that allows to create more dense heat sinks. On the one hand, more dense meaning more contact upper vlek, reaching higher velocities within the part itself, that improves the heat transfer. And on the other hand, you have a secondary effect of improved heat transfer through the conductivity that is significantly higher as well for the EC10 compared to the traditional PG25. So 20%, if you ask me, I was very surprised by the impact of this. I was not expecting this significant numbers, but this is definitely, if you ask me, definitely something worth exploring more in detail and exploring and seeing what the impact would be at system level of this, because 20% is not a number you can actually ignore, if you ask me.
Mm-hmm.
Voila, Senne.
And that's great to see, because we believe that, based on all of this that we've seen and we investigated on, is that the direct-to-chip cooling that uses the water-based coolants and the cold plates have not yet reached its limits. And by optimizing actually both the fluid and the hardware, the cold plate design, we can generate improvements in the heat transfer on one hand, but also in the heat reuse and also on the pump efficiency level. And this will allow a higher output with a lower energy usage and driving the PUE down and the sustainability eventually up. There you go. This was our joint webinar. Thank you very much, Lieven.
Thank you, Senne.
And if there's any questions from your side, please have them in the chat and we're happy to answer them.
So just as a reminder, and this webinar will also be shared as a recording with all of you. So you have all the opportunity to rewatch it afterwards. And like Senne mentions, if you have any questions, drop them in the private chat or the public chat, depending on whether you want anyone to see that you posted that question, and we're more than happy to answer them. Okay, I have here one question coming in with respect to the design itself. So linking back, let me circle back. So the question itself is actually linked to the summary where, and the question is, how can it help on the pump efficiency when the operating point is actually the same? It's obviously very relevant question. So remember when we made the design, let me circle back to the right slide. Well, almost there. Yeah, voilà. So when we made the design, like you see here, the design target was set to a pressure constraint of 7 kilopascal. Obviously, the pumping power and the pump efficiency is linked to the combination of the flow rate and the pressure drop that the pump needs to deliver. You can perfectly adjust the design process to either minimize the pumping power or to design at a different, for a minimal pressure drop, for instance, for a given maximum temperature. So there's the illustration you have seen here is just one illustration of how our generative design technology can be used. But there are many different combinations. In total, more than 20 objectives and constraints are available to drive the design process. Maybe next question, Senne, maybe for you from Tabish.
I can take that one. So the question is, how effective is a PG25 product compared to a water glycol 50/50? So a PG25 product actually consists of 25% propylene glycol with give or take 75% of water. So comparing that with a 50/50 glycol water, then definitely a PG25 type of product will score better on thermal conductivity, specific heat, and will also have a lower viscosity than a product with higher glycol. Because all of the low viscosity comes from the water, and the good thermal conductivity and the good specific heat also comes from the water. So the more water you have in your mixture actually will increase and will make your fluid better on these aspects at least. Yeah.
Okay, and then we have another question through the private chat on the use of two-phase pumped direct fluids. So maybe to comment on that from Diabatix point of view, Coldstream is perfectly equipped to design for two-phase coolant as well. We have done several public studies on that. We also have a series of customers focusing on that type of work within the platform. So instead of selecting then these the three coolants you see here on the screen now, you can perfectly select a coolant that evaporates, and then the evaporation and so on is taken into account properly during the design process. You can actually see what we actually actively can create and the designs for a boiling liquid or a condensating liquid as well. Maybe I don't know if from Arteco side there's something you can add to that.
Well, on the two-phase type of product, the thing is today that there's with these type of fluids or products, the main concern is environmental and health because of the PFAS that it contains. and that's definitely not something Arteco wants to contribute to. So we're not diving into anything that contains PFAS. But the investigation on an alternative, maybe water-based, is something that we are investigating on, because it could definitely have potential if you see that the heat capacity is actually much higher with a two-phase type of product than with a water-based one or an immersion one. It could definitely have its value in the market if the challenges, of course, are overcome with the design, for instance, as well, which is very complicated. So yeah, investigation is running on that, and we'll see what it brings.
Okay. Also, from design with respect to design, another question that I see popping up: what are other shapes that you can that could be interesting for this for chip cooling? Well, it's hard to answer in let's say a very general way. So as illustrated here on the slide, we have a wide range of plates that are supported by default. So depending on where the inlet and the outlet are positioned, some of these will work very well, others will not work properly. But that's obviously why we developed Coldstream, is to explore and what could be of good use to you. And obviously there's always opportunity and the option to go for a more custom design approach or very organic design approach, if that would also fit within the scope of the product that you're designing. So it's difficult to say up front, okay, this is the best shape to say, but we have developed the perfect system to explore that, as illustrated. Evaluating 1,000 designs in less than 2 hours, that's computing time. It actually takes less than 10-15 minutes to configure everything by the engineer and pressing the start button. Voila. If there's any other questions, now is the time to share them. If not, then I would like to thank everyone for their attendance. As mentioned before, the recording will be shared over email, and we will also follow up to see if there would be any further inquiries that you would like to discuss with either us or with Arteco. If someone would also be interested in joining our technology integration program, like you see here with Arteco, this is one of the outcomes of that joining the program. Don't hesitate to reach out to us as well. All right, thank you very much, and have a very nice day, everyone.
Thank you very much. Bye-bye.